Hi, it's Paul with the first of the scripts for week 2 of Math 156. I'd strongly encourage you, before going through this video, to read through pages 13 to 24 of the textbook, because what I've tried to do is to illustrate how many of the tables and graphs in that part of the textbook can be produced by using R. So, you've read the book, right? You've restarted the video. And this first bit is going to be familiar from the first class. What I'm going to do is load up from the CSV file in your data directory the flight delays data frame. If this line doesn't work when you try it, it means you haven't set up your working directory correctly, and you'll have to go to Tools, Global Options, and do that correctly. But once you've got it read in, a good way of peeking at a data frame is to use the function head, which will show you all the columns but just 6 rows, which fit neatly in the display below. If you want to know how many columns there are, ncol. If you want to know how many rows there are, 4,029. You wouldn't have wanted to find that out by scrolling through them, would you? If you ask for dim dimensions, you get rows and columns one after another. Flight delays, being a data frame, is actually a list of columns, so if I ask for its length, I get the number of columns, which is 10. But if I pick a particular column, say the month column, and ask for the length of that, since that's a vector, I get the number of rows, which is 4,029. If you have a categorical column, which consists of strings rather than of numbers, and you ask for a table, you get a list of all the values that appear. Those are the airports to which the flights go, and the number of times each value occurs. A nicer way to look at this is to ask for a bar plot, which you see over on the right-hand side. Frequently, what you want to do is make a so-called contingency table comparing two of these categorical columns. So if I provide table with 2 arguments, I get a nice table showing the number of flights broken down by the destination airport and the carrier, either American Airlines or United Airlines. Okay, I've shut off my phone and resumed. If we make a table showing carrier and flight number and look very, very carefully, you will see that there's one and only one column in the middle row, flight 745. That is a number that's used both by American and United. Now let's look at the really important feature of this data frame, the flight delays. And I want to make a vector of the delays, so I do flight delays $delay. That extracts the delay column from the data frame as a vector. I can ask for its median. The median is negative. That's no accident. What airlines do is set their departure time a little later than what they actually are hoping for, so that the majority of their flights will appear to depart early. But as anyone who flies knows, if you ask for the mean delay, that's definitely positive, and the reason is that there's the occasional very long delay. If I get rid of the 10% of extreme values at either end, then the mean becomes very close to 0. If you want a lot of stuff about delays without having to ask for individual items, just call the R function summary. You'll get means, minimum, quartiles, median, whatever you like. Now have a look carefully at page 19 of the textbook. That explains all about box plot. If I do a box plot of delays, the feature that is most prevalent is the outliers. That long strip going up to the top shows those delays of 700 and 500 minutes. Down at the bottom, the horizontal lines show the first and third quartiles, and the median in between. That variable was extremely skewed. The distance in miles for the flights, that's in the flight length column, is much better behaved. And if I do a summary of that, and then equivalently do a box plot, you can look at the box plot and see how it illustrates the fact that the median, which is 163, is much closer to the first quartile, 155, than to the third quartile, 185. I won't say any more about box plots, but they are a useful way of visualizing graphically the details of a non-standard probability distribution, and you'll probably want to read about them more carefully. I want to move on to the subject of conditioning on one of these categorical variables. And to do this, I discovered for myself the wonderful R function split, which is neither mentioned in the text nor in the tutorials. What I'm going to do is split up the delay according to the categorical variables in the carrier column, and that splits it into a list of vectors. In this case, one for each carrier, one for American Airlines, one for United Airlines, and I can ask for the mean of either of those by mean of SPL $AA for American, and so on. So there are the means for the two different carriers. If I use lapply to split, since split gives a list, lapply applies to each element in the list, and I get the same information, the means for American Airlines and United. Alternatively, I can do everything in one line by first doing split to create a list and then lapplying mean to that. I confess I cannot remember the syntax for all these applied functions, so what I do when I need the results of an apply function is I find a script where it's worked correctly, I copy the line out of the script, and then apply it to the data at hand. You can even split on multiple factors. If you want to know how delay breaks down when you break down according both to the day of departure and the carrier, you can do that in one line, and the result you get is a bunch of delays, each labeled both by the day of the week on which the flight occurred and the carrier for that flight. You can do the same thing with box plot, and this is not a bad way to get started with a new data set. Here, data equals flight delays says we're working with the flight delays data frame, and we're asking for delays conditioned on, that's what the tilde does, carrier. And you get a nice box plot separately for the American Airlines and the United Airlines data. If you do this by day, you get a box plot, one for each day of the week, and you can see that for whatever reason, the third quartile looks significantly larger on Thursday or Friday than on any other day of the week, and two of the three most extreme outliers appear to occur on Sundays. Do the same thing with departure time, and you can see that you seem to get longer delays for flights leaving between 4 and 8 p.m. That certainly is in accordance with my experience as an airline traveler. Now suppose you have a data frame and you're not interested in all the data. Suppose, for example, you're just interested in flights that go to O'Hare Airport because that's the only destination that American and United have in common. So we make a new data frame, flights ORD. Why ORD is O'Hare, I don't know. And you ask for the subset function where what you want is the subset equals destination equal to ORD for O'Hare. So now you've got a new data frame, and you can ask, give me a contingency table broken down according to day and carrier just for flights to O'Hare. And there you have the results broken down, number of flights for each day of the week for American and United, respectively. If I now want to figure out what the mean delay looks like on that basis, I ask to tapply, I think that's short for table apply, the mean function broken down by both delay and carrier, and what I find is that the mean delay is somewhat greater for United than for American. If I break it down by day, I can find the mean delay for each day of the week. That looks fairly reasonable, and it's in accord with our earlier observation that the largest delays occur on Thursdays and Fridays. The main point of all this is that once you have your data set in an R data frame, you can learn an awful lot about it with a few simple commands, and you can present the results graphically. For example, you can present the recently obtained results about delays on day of the week as a bar plot. Now, getting back to more probabilistic ideas, we're now going to create some experimental cumulative distribution functions, ECDFs, and I strongly recommend that you pause the video and read section 2.5 of the text before moving on. You're back, right? So let me start with the probability example that's not in the textbook. Remember, in the very first class, I created a data frame for rolling 3 dice, and I saved it as a CSV file, which is in the extra data sets for the course. And I'm now going to read that back in, and I'm going to create a new vector, which is the total roll. If I want to display the results for the total roll, I just use the function table, and that, I believe you've already seen this before, says there's 1 row where the total is 3, 3 rows where the total is 4, and so on. Conveniently, if you ask for a plot of a table object, even a table object divided by some number, namely the sum of the totals, which will make these probabilities sum to 1, then I get a plot of the density function where the probability is represented as the length of a vertical line. This is a little bit tricky, as you'll discover, to do by hand, but it happens automatically when you're working with tables. Now we're going to work on the cumulative distribution function. That's the probability that a certain random variable has a value that is less than or equal to some real number. And when I plot that, you can see I get a function whose values go from 0 to 1. The probability of being less than 0 is 0. The probability of being less than 18, of course, less than or equal to 18, is 1. And this plot rather nicely draws a horizontal line for each possible value. As a mathematician, I feel obligated to point out that this function is neither surjective nor injective. It fails both the requirements for being invertible. You can do the same thing with real data. Let's look at this wonderful beer wings data set. And on looking at head, you are reminded that this shows for various patrons in a Minneapolis pub how many hot wings they ate on a Saturday night, how many ounces of beer they drank, and what their gender was. And of course, we're going to split up the beer consumption by gender and discover that females average 22 ounces of beer, males average 30 ounces of beer, from which the lesson is to draw is stay off the roads in Minneapolis, and you're not that much safer just because the driver is a woman. An alternative way of getting this is splitting up and then using lapply to get the mean for each gender. Sometimes you have a column in a data frame and you don't want to turn the whole column into a vector, you just want to turn a subset of that column into a vector. And You can do this by using the subset function in R, for which the syntax is a little bit tricky. Your data set is beer wings, and what you are selecting is the beer column. That's the number of ounces of beer. But you don't want the whole column. You just want the subset for which the gender column has an M in it. And you want the result to be a vector rather than a new data frame. So you say drop equals 2. And now you have a vector with just the data you want. I discovered that I can achieve the same effect by splitting this up by gender, splitting beer up by gender, and then using $M to get just the M values. You can see below I got exactly the same results. I can plot this, and if I plot the value in the table divided by the sum of all the entries in the table, I get some numbers that sum to 1, and this is a perfectly good probability density or probability mass function, giving the probability of a certain male having drunk a certain number of ounces of beer on that Saturday night. If you want, instead of the density function, the distribution function, you call plot.ecdf. Now, if you're really interested in gender issues, you probably want to put the male and female data on the same graph. It's not too hard to do this. Here is beer female, a vector obtained in the same way. But what you need to know is that this is a so-called high-level plot, and if you just plotted the female data, it would overwrite the plot. You can get around that by saying add equals true. And so if I ask for the ECDF for the female data, I get it overlaid with the male data. If I don't say add equals true, I get the female data alone. How did I get that different symbol? I used PCH equals 2, and you have to look up in the documentation what symbol you get for what value of PCH. Now, a word of warning. I said add equals T. This is a popular way of abbreviating true, but it's very risky because true is a reserved word. You can't say true equals 3. T is not a reserved word. It's a variable whose value is initialized to true, and if at some point you assign the value 7 to T, it won't be true anymore. I've had summer school students who spent hours trying to figure out what was going wrong with data they got in another course because the instructor had used T instead of true, and then in my course they had set T equal to some value that was different from the logical value true. So I generally write out true as 4 letters to avoid that risk. Now, you might say, to get a view of how the distribution depends on gender, it might be a good idea to rescale them as if the women had drunk the same average amount of beer. We can do that by multiplying by the ratio of means for males and females. And notice this is a nice example of a vector operation in R. Each entry in the beer female column gets multiplied by the ratio of beer consumption automatically. And now when I do that, I can plot the male data, overlay the female data on that, and that's probably the best display that I can come up with for trying to indicate whether the distribution function for male and female beer consumption is the same. So that ends this introduction to exploring data sets in R. As you explore your own data sets, you'll probably want to refer to this script to find the commands that you know produce the desired results.